So, linear regression and machine learning part 4. In this video, we're discussing polynomial regression. Polynomial regression is not, strictly speaking, a linear problem, but it can be efficiently solved using the instruments of linear regression, which we already know. So, the idea is to approximate our target variable y by a polynomial function based on scalar feature x. This is now a polynomial function, not just wx plus b as we considered it before, but it's a polynomial of some degree p. So we have a free term b, which is bias or intercept, better to say intercept in the context of this video, and w1, w2, wp are some weight coefficients, polynomial coefficients. So it may seem a difficult problem to consider, but it makes at once very easy once we consider the powers of x squared, x cubed, x to power p as new features. And then we apply multivariable linear regression, which we considered in the third part of these videos. So again, these powers of x will be just new features. And then we use apparatus of linear multivariable regression. I propose to consider some set of test data, 50 points of test data, or 50 points, which are subdivided into training and testing parts, and we will use 10 points for training, as is shown on the right part of this slide. So we can apply first-order polynomial approximation, wx plus b, and we can see that on the left for p equal to 1, so it's linear function, it provides quite a poor approximation, both for training and test data. So this phenomenon is called high bias. Once we take the second-order polynomial approximation, the approximation is a little better. Yes, some parabolic tendency in the red approximating line, but still we have a high bias. And you can see also the coefficients of w and b obtained, polynomial coefficients w and intercept b. So, but still we have a high bias. Bias becomes definitely lower once we take approximation, for example, of third and fourth order. But I want you to take notice that the coefficients w start to grow in magnitude. Yes, you can observe already w for p reach 55, minus 55, minus 53. And this tendency is going on. For example, for the orders of polynomial of 6 and 8, you can see that approximation and error correspondingly, training and testing error become lower, but the coefficients start to grow quite significantly. And for p equal to 10, the situation is very interesting. The 10 training points, of course, by the 10th order polynomial are approximated perfectly by 10th order polynomial regression. But for testing points, we start already getting quite a large errors. And this is also accompanied by the growth, very significant growth up to 900,000 of coefficients w. Although intercept b remains here quite small. So, and this tendency, of course, keeps going for the higher order of polynomials, like 12 shown here on the right, and for 20. So this phenomenon for 16, 20, this phenomenon, when we have a low error for training data, but a very high order for independent testing data, which did not take part in the process of training. This is called high variance of a learning algorithm. Or also it is called sometimes overfitting. So this is an observed phenomenon. And if we plot the training and testing error depending on the polynomial degree, we see that the training error quickly becomes zero with the growth of polynomial, order of polynomial, but testing errors start to grow. This is overfitting. This is the phenomenon of overfitting. So, again, high bias means that we have poor approximation both for training data and for testing data. And high variance means that the error for testing data becomes very high, although the error for training data would be quite low. This is high variance. So usually the machine learning algorithm must keep some balance between bias and variance, and we will in the following consider how to deal with it. So how to deal with high bias? We can try getting additional features. Yes, we can try adding polynomial features as we have just observed. But adding more training data usually doesn't significantly help. How deal with high variance? We can get more training examples, of course, and try smaller set of features. Because we just observed this phenomenon of high variance when we started growing, when the polynomial degree started growing, more features were involved. We can try a lesser set of features, for example, 6, 10, 8 in this example. And also very important concept, try regularization. What is the idea of regularization? The idea of regularization is to prevent the growth of coefficients W, which this growth makes our solution of the problem unstable. So we can strive to penalize the high values of W. How can we do this? By regularization. What does it mean? Remember our cost function for multivariable linear regression, which is shown on the upper part of this slide. And we can add into it one additional term, so-called regularization term, with the coefficient lambda and the sum of squares of WK, weight coefficient, polynomial coefficients WK. So if we want to minimize this cost function, we are simultaneously minimizing the part corresponding to usual part of multivariable linear regression, the first part of the first sum, and the second sum, which will help us to minimize the values of coefficients W. So some kind of compromise. We're striving to minimize our cost function, usual cost function, at the same time trying to keep the coefficients W as small as possible. So some kind of compromise, some kind of regularization of this problem. This is called also trick of introducing this sum of squares of W is called rich regularization. And lambda is called regularization parameter. Gradient descent, we can easily take derivative of this cost function, and gradient descent is slightly modified. The equations for B remain unchanged, but into the equation for W, one additional term, lambda multiplied W divided by also by M, although M number of observations can also be included into the lambda. And this is just a small update in the equations for update of coefficients W in gradient descent. Very small update. So, of course, it can also be quite efficiently vectorized, as we usually observe. Again, equation for B remains unchanged. I would like to show a few examples. So, the effect of regularization. For example, we can see example of regularization by high order polynomial. Maybe it's 10th degree polynomial on the left. Without regularization, we have very high test error in opposed to almost zero training error. And a training error with regularization parameter of 0.0001, 1/10,000 makes test error quite lower. Of course, training error also becomes higher, but nevertheless, this is a good compromise because we are interested in the algorithm which generalizes well, which works well both for training and test data. So this regularization provides a quite significant effect. And again, plot of error without regularization and with regularization of lambda equal to 1/10,000. So before making some conclusions, I would also like to show you how it works in Colab. In Colab, for example, I take fifth order approximation for our points. So it looks like this. This without regularization yet, without regularization. But if I take, for example, 15th order of polynomial, or maybe 14th, I have a very high error for testing. And this is a graph plot of test training and test error. Training error becomes almost zero, while testing error is quite high. What algorithm I'm using? I'm using linear regression algorithm, exactly which we have programmed previously. But now I would like to add this regularization parameter lambda. Yes, 1/10,000. And here is function for linear regression. Let me show you where the gradient is. Yes, here the gradient is computed. No, this is for not the gradient. This is for additional term for cost function. And the gradient is one term. This term with lambda is added into the gradient. Let's make it big font. So, and of course, the basic equations for gradient descent remain unchanged once we have computed gradient, taken into account this regularization parameter lambda. Let us show how now it works. No effect. Why? Oh, because another branch of the code was activated. Okay. Yes, now we have approximation by the 14th order, and we have quite decent error both for training and test data set. And here's a graph of this, of dependency of this error, testing and train errors, depending on the order of polynomial. I can also take, for example, the 20 up to 20th degree. Let's see how it works. No, it's starting. Maybe I'm using just a little amount of iterations for gradient descent. It does not converge properly. I will use for this example. I will use built-in. Where is it from? From a scalar function for linear regression, for regularized regression. Where is it from? From a scalar, yes, from a scalar library. I will use built-in function. No, because I did not use a regularization parameter for it. I put it zero. Now it should work. Yes, now it works. And we can see both good training and test errors. Of course, training error is a little less than the training error, but now it's like a compromise. It's a decent compromise between maybe between bias and variance as well. Okay, let us return to our presentation. To summarize, so how we're dealing with high bias? We can try getting additional features, maybe polynomial features, and we can decrease regularization parameter if we already use regularization. and adding of new data usually doesn't help much. How we deal with high variance? We get more training examples. We try to use smaller sets of features, and we can increase or use, if we didn't use before, regularization parameter. This is how I'm dealing with high variance. So we considered polynomial regression. We encountered with the phenomenon of high bias, large error for training data, and high variance, large variance for testing data, and how to make compromise for them using the apparatus of regularization, or penalizing the growth of weight coefficients, polynomial coefficients. Thank you. Again, thank you very much for your kind attention.